Why are some of these things already filled in?
That's the same as tangent.
Exactly. What's the same?
The period.
Period.
The domain.
The domain.
The range. And the system.
Okay. That's like the majority, right? What's the one thing that's different?
Vertical asymptote.
So maybe the domain will be a little different too, but the idea is the same. X's are everything but the vertical asymptote. So, does anyone remember back to that table that we wrote down in our notes with formulas where we said sine, cosine, tangent, cosecant, cotangent from X's and Y's, how we found them? What did cotangent equal? X's and Y's, it's like ordered pairs on the unit circle. Do you remember? Look in your notes. What did tangent equal? Wrote it down for tangent, right at the beginning of this section. Tangent equals, right here by the circle.
Oh, y over x.
Okay, so tangent is y over x. Cotangent is going to be
X
over
over
y. There we go. See, you got this. So cotangent. So when will cotangent, you're spelling in. So when will cotangent be undefined? Because vertical asymptotes happen when there's an error. There's going to be an error when who is 0?
Y.
So we can say is undefined when y equals 0. It's as easy as that. For what points, indicative of what angles, will y be 0 on the unit circle? When's the y 0? Not at pi over 4, not at pi over 6 or pi over 3. Pi over 2, wait a minute, look at the tangent circle. I think we wrote down pi over 2. The x is 0 and the y is 1. No, we want the y to be 0. When's the y 0? Good, on the x-axis, which happens either at 0, right? Which has the ordered pair of 1, 0. Or at, what's this angle over here? 180. Good, 180, or? 2 pi. Pi. 1 pi zone, remember? Negative 1, 0. So when y is 0, the x's are 1 and negative 1 doesn't matter, but the y is 0. Ooh, that's not going to work out so hot when we go to plug in. Now, you're right, 2 pi would actually also be a problem, because isn't this 0 or 2 pi? And couldn't this be 3 pi? Wouldn't that be 4 pi and 5 pi and 6 pi and 7 pi? How many vertical asymptotes will cotangent have?
A lot.
Infinitely many. Because 0, you haven't gone anywhere. Pi, you've gone here. 2 pi, you've gone all the way here. 3 pi, you keep rotating. 4 pi, you keep rotating. 5 pi, 6 pi, 7 pi, 8 pi.
16.
So, exactly, would be, cotangent would be undefined. How about negative 7 pi? Yeah. How about 3 pi over 4? No, he's not on the x-axis. The only angles on the x-axis will be the whole pi's. So how do we write that? We say there'll be a vertical asymptote at x equals all of the, it's a crazy way of writing it, but all of the pi's. We kind of use this notation for tangent if you want to go look at it. Except with tangent, we said start at pi over 2. You got to start removed, and then you got to add pi, add pi, add pi, add pi, or subtract pi, subtract pi, subtract pi. Because tangent would be undefined here and any pi away, positive or negative. But for cotangent, we don't really have to go anywhere. It starts off being undefined, and then we add pi, add pi, add pi, add pi, or subtract pi. Subtract pi, subtract pi. Remember, this just means multiples of pi. Like, my first vertical asymptote, 0. Is 0 a multiple of pi? Yeah, sure, 0 times pi. What would be my next vertical asymptote?
Pi.
1 pi. My next vertical asymptote?
2 pi.
We can keep on going however long we want. What if we go the other direction? My previous. Do you guys get the idea? Pi n is a snazzy way of just saying all the whole pi's. Because n would be an integer, and integers are whole numbers. No fractions, no decimals. N would be a whole number, like positive 1, positive 2, positive 3, negative 1, negative 2, negative 3, including 0. Now, what did tangent have? If you look at the tangent graphs, we did it yesterday. What does tangent have halfway between all of their vertical asymptotes? What's halfway in between all of tangent's vertical asymptotes? What did we do halfway in between? What did we do halfway in between? And an intercept. Or an intercept. And an intercept will always technically be with the sinusoidal axis. If you want, come back to your tangent for just a second. We didn't actually write about this point at all. So there are going to be vertical asymptotes, and so that's what we wrote down yesterday. Find the vertical asymptotes first. What we didn't technically write down is that you can also find what I call a POI, a point of inflection. POI, a point of inflection. There's going to be a point of inflection halfway between the vertical asymptotes at y equals d. So just like sine, how sine starts in the middle, sine starts at d, technically tangent and cotangent halfway in between their vertical asymptotes will always be at d. Which, if there is no d like this one, d was 0, no addition going on, fine, it hits at 0 or on the x-axis. And guys, is there a d in this equation right here? No. So where's it going to hit halfway in between? On the x-axis again. That's not very halfway, is it?
No.
What would be, like, what would I mark halfway in between 0 and pi?
Half pi.
Half pi, good. It's going to hit, cotangent's going to hit at half pi. And then over here it's going to hit at negative half pi. If I count by halves, what would this one be?
Pi over
Yeah.
2.
3.51, 1.52, 2.53, do it that way. Or 1/2, 2, sorry, 1/2, 2 halves, which is 1, 3 halves. Just counting by fractions. Another point of inflection. And why is it called a POI? Why is it called a point of inflection? It inflects, and what that looks like on a graph is it goes from one concavity. What kind of concavity is before for a tangent?
Downward.
Yeah, it looks like a frown kind of, right? So that's concave down. It goes from concave down to concave up.
Happy face.
It's okay, here's your happy face, right here.
Oh, yeah.
There you go. Concave down like a frown to concave up like a smile, and it doesn't work. Concave up like a cup. Okay.
Ooh, I
Concave
like
down,
it.
concave up.
Like it.
Now, the weird thing about cotangent, he's not just shifted. See how his vertical asymptotes are naturally not around the x-axis? They've been shifted, so it's actually, around the y-axis. It's actually been shifted. Cotangent not only shifts, but it also flips. So it's going to go concave up to concave down. That's fancy. Tangent's a happy guy, cotangent's not. Tangent's always going up,
I like it.
cotangent's always going down. Unless they get flipped, and then of course, if cotangent gets flipped, reflected, well then he'll be going up. If tangent gets flipped, well then he'll be going down. We could go into give grace to people who are usually happy when they're not happy. We could go into encourage people that are usually pessimistic when they are optimistic. Because even though your natural tendency might be to be one over the other, does not mean that by grace you can't change. But we'll just stick with the tangents and cotangents for right now. So, how similar now? Hold on. This guy was transformed a little bit, right? Wasn't he stretched, I think? He was horizontally stretched a bit. The better one to look at, to compare, would be the normal tangent before the transformations. But no matter what you're looking at, kiddos, how similar are tangent and cotangent?
They're just sitting in opposite chairs.
Kinda. Oh, kinda. Opposite chairs. Like on a train where they're facing each other.
Michael's got this.
Okay. So tangents going one way, cotangents going the other, but they both have points of inflection. Those points of inflection will always happen halfway in between the vertical asymptotes. And they both have ways of finding their vertical asymptotes. If you are a highlighting kind of person, or a marking with a colored pen kind of person, for tangents and for cotangents, one of the biggest keys, like memorization things you should do, is how to find their vertical asymptotes. Now, knowing the shape of the graph, yeah, tangent's optimistic, cotangent pessimistic. That might be helpful as well, but one of the big memorizing things for tangent and cotangent is where are their vertical asymptotes. So when we go to cotangent, second page, the very first thing we're going to do with him, same thing as tangent, but instead of taking the argument, whoever's inside the cotangent, instead of taking that and setting it equal to tangent's vertical asymptotes, we got to take whatever's inside and set it equal to cotangent's vertical asymptotes. And cotangents, vertical asymptotes, are just gonna be pi n. So that's what I'm gonna highlight over here. Tangent, I gotta take the argument and set it equal to pi over 2 plus pi n. Cotangent, I take this guy and set it equal to pi n. And technically, if we were to write like everything out, the other one we'd write is the POIs. What does that stand for again?
Point of interest.
Inflection.
Oh, my
Person of interest, that's close, right?
Yeah.
That's point of interest, we did that.
Yeah, it is, I watched.
There you go. Point of inflection in math. Gotta have some points. Anyway. Point of inflection is going to be the exact same as tangent in that once you get the vertical asymptotes, which will be different than tangent because they're shifted. But once you find the vertical asymptotes, we can still go halfway between the VAs, between the vertical asymptotes, at y equals d, if it's there. Almost always, tangent and cotangent very rarely get vertically translated. But if they are, we'll know what to do. Point of inflections will always happen halfway in between. Now, if I was super, super picky, sometimes I am, but not really on this. Algebraically, yeah, because you can't have one number and then pretend it's right when there's really another number, that's true. But with tangents and cotangents, guys, if there was something like a normal tangent, I'll just say tangent of x, let's get rid of this, that was calculus, even though it looks easy, it's kind of hard. Here's our pi over 2. And our negative pi over 2. I could have to get out your calculators, but you guys always make a big deal about it. Anyway, long story short, there's a tangent. My question to you is, what do you think is going to change when we do something like throw in a 4 times? What's going to change if there's a stretch? It's kind of going to move up. What's going to happen to my concavities? Because right now you can see the concave down pretty clearly, right? And can't you see the concave up pretty clearly?
Yes.
But what's going to happen if we vertically stretch it by a factor of 4? Just think, if that was fluid, meaning it's movable, like a piece of string, what's going to happen if you pull it? It's going to become less curved, aka more straight, right?
Oh.
So it's going to be something like, right? Something like that. What would happen if instead of a 4, well now I need to make this, let's do 4 divided by
7.
3, 6, 6, 6.
Yeah, we'll do something like 15, that way it wouldn't have to reduce it, because some of your numbers you have to reduce. Okay, long story short, this way you don't have to reduce it. 4 over 15. For the original tangent, didn't it just get shrunk?
Yes.
Yeah.
So imagine that you pushed it, what's going to happen?
It's going to shrink
It's
this
going
way.
to shrink
It's
again.
going to shrink, what's going to happen to your concavities, to your curvature?
More concave.
Yeah, it's going to get
Is concave the word?
more curved, does that work?
I like that.
Or it's going to become depressed?
Yeah.
That sounds not quite right, but anyway.
What if we push it so
That makes
much that it
sense.
just becomes a straight line? Horizontal.
It's possible. But the problem is, isn't it eventually going to have to go down?
Doesn't that mean it's just going to be
But
extra
you,
close?
depending on what you look at, you won't know it, right? You have to make sure
If
your
you want a
window
line,
shows
just
you
do
it.
twice the- Exactly, isn't it?
And then if you keep on pulling it, couldn't it look like a straight line?
I mean, it could, but
It
it's
could.
illusion.
Okay.
If you want to.
Here's the point. Pause. Ready? I'm not going to make you guys, technically if I was a really mean teacher, I'd be like, you know what, the point of inflection is not enough. You need to find some angles in between each of the intervals to figure out exactly where to hit. Do you hit here? Do you hit here? Do you hit here? Okay, but I'm not like that. Instead, listen, for tangents and cotangents only, I let you be a little wibbly wobbly on it. A little bit like, let's just pretend. And here's what I mean. If there is a big number in front of tangent, if it's been vertically stretched, should that be very curved? If there's a big number in, like 4.
No.
No, it should be, don't draw a line. Well, depending, if there's like 100, maybe you should draw a line. But don't draw a line. Show me a little bit, but just a little bit. That's it. Okay? If it's normal tangent, you can just show me, all right, just a quick little change. But if there's some sort of like 1/2, 1/4, 1/10, what should you be showing me?
Concave.
Really obvious leveling off. Now, I'm not going to make this a big deal. Might be worth like 1 point out of 100 on a test, maybe like a half point. Well, most tests are 100, right? We're coming back. Actually, I think you only have a quiz on this, and then it's on the final. Like this section 4, 5, 4, 6, 4, 7. But coming back, I'm not going to make you do or find separate trig angles in between every single point, as long as you make sure that when you're showing me the concavity, you don't have it be super flat if it's something like 10 tangent. That doesn't make sense.
No.
Because 10 tangent, that little curvature is barely there. Does that make sense, kind of?
Mm-hmm.
As long as you get that idea down, I'm good. Kiddos, if I were you, you might want to write that somewhere down. Basically telling yourself, if there's a vertical stretch, the curvature is very slight. And if there's a vertical shrink, the curvature is very clear. Does that make sense?
Yes.
If there's a vertical stretch, the curvature is very slight. The inflection is very slight. And if there's a vertical shrink, the curvature needs to be very clear. Okay. As you guys write that down, I'm going to go ahead and get all of my tools up here in the right spot and zoom in on this transform cotangent function. Zoom in on this transform cotangent function. And to be honest, I don't think I need to show you guys cotangent and tangent because they behave so similarly. So when I'm talking about tangent's curvature, I'm also referring to cotangent's curvature. If there is a vertical stretch with a cotangent, the curvature will be very slight. If there's a vertical shrink, the curvature will be very clear. Okay?
I have a question. When did Afghanistan become a state?
I was gonna ask that. Wait, where are you
Wait.
getting that from?
What happened?
You should ask, actually, hold on, wait a minute, someone changed it. I would say Alan Lovett, he's usually the state of the day. And then, who would come in and then?
No, was it Chinese, right?
I always talk about,
It
was Jason and Caleb I was talking about. It was Nathan Bennett's brother.
Jason and who?
Taylor. Oh, Tyler.
Caleb. Yeah, ask Caleb.
It might have been.
Go back
Tyler.
I'm sorry.
My fault.
Tyler was here. Ask Jason, Tyler, or Caleb, and then you can see whether or not you agree with what they say.
Afghanistan, that's a good idea.
Yeah, it's good to compare.
Alright, here we go.
I'm a really big fan.
You did a reason before the day ends. Sorry, after school, who knows what happens. Anyway. Guys,
Colors.
is there any shifting going on?
No. Yes.
Yes.
Shifting? Any translating?
Yeah.
No!
Oh, I was right the first.
Any translations happen? Added or subtracted, right? Do you see any addition or subtraction? No. Me either. Okay. But pause. It's not making you write out all the different transformations, but if it was, you would have a vertical stretched by a factor of 2. Ooh, so the curvature is very slight. Good. Well, fairly slight, maybe not very slight. Curvature is slight and a horizontal, ooh, what? Shrink or stretch?
Stretch.
Backwards, what you think? Stretch by a factor of 3. So it's going to go, but my clues just say, hey, take that guy. Take the inside of cotangent. Leo, what? Notes open, go. Okay, so x over 3. X over 3. What do I set? Whatever's inside, whoever he is, whatever's inside cotangent, what do I set it equal to for my VA? 9.
Oh.
This comes from the function, that comes from, well, vertical asymptotes at cotangent are always naturally a pi n. So then, AJ's already like, well, okay, just multiply by 3, right?
She's like,
So therefore, hey, where are my vertical asymptotes?
I'm so bad.
3 and
You didn't even hear me ask you, that's
I
sad.
got
Hey,
it.
where are my vertical asymptotes?
I have no idea.
It's in
I know, AJ already answered, I was gonna steal it, go.
3 pi and 3 n.
3 pi, and every 3 pi. Starting at, well, then is 0, okay, fine. But then, if n is 1, question, where's my next vertical asymptote? 3 pi, yeah? Every 3 pi. Where's my previous vertical asymptote? Negative 3 pi, there we go. Are we tracking? Good. How did I find that 3 pi? I took the inside, like my formula tells me to. I took the inside and I said it equal to where all the vertical asymptotes are normally. Multiply by 3, okay, there they all are.
Wow.
But how am I going to keep on graphing my cotangent with very slight curvature? My poise. Where are they?
Somewhere between the VAs and the Y equals
Okay, so where's that going to be? Oh, there's one, yeah, right. Okay, how would I label it? 3 pi over 2. Take the 3 pi and cut it in.
You know what? You know what? This person should be an AP, not an AP.
Honors. Okay, so where's this one going to be?
I think it's 3 pi over 2.
Got it. Cotangent, is he optimistic or pessimistic? Is that
He's a
correct. So therefore, slight curvature, but I still have to go in between. Slight curvature, but I still have to go in between. That was pretty slight, maybe a little too slight.
Oh, good.
You guys are giving me grace like I'll give you grace on the grading?
Yes, yes, please.
But either way, cotangent, going down. Going through the point of inflection, has to have some sort of curvature, but fairly slight. It's been stretched a little bit, right? How are we doing? Good. I don't know.
Awesome.
Tan cotan, if you have the highlighting down, and you remember the poise, in which direction to go, you should have it, right? Okay. So to finish off today, let's go ahead and say, wait a minute, the whole bouncy, bounce, bounce, bounce ones, we gotta go figure those out too. Cosecant and secant. Oh, come on, you saw them yesterday. If we know the sines and cosines, all we have to do is future. We got them. Now, we only have a few more moments with our AP language people, so hold on. Let him get this down. Secant and cosecant, I'm putting all on one page because they are so similar. How they move, how they behave. So is tangent and cotangent, but their vertical asymptotes were separate, so we just did them separately. Cosecant and secant, one big page to get down the main ideas. I'm not going to have you guys go ahead of me this time, but you're just going to kind of stay with me. Cosecant, if we were to use those XY formulas, cosecant, who's 1 over sine, would be 1 over y. And 1 over y will be undefined, or have VAs, when y equals 0. Wait, we just talked about y equaling 0 with cotangent. Because cotangent had a y in the denominator also. So where were cotangent's vertical asymptotes? At all the pi ends. So guess where cosecant's going to have all of his vertical asymptotes? At all the pi ends too. Oh. Because any function with a y in the denominator is going to be undefined at all the pi ends. We could go through the unit circle and remind ourselves of y. But long story short, whenever y is 0, both cosecant and secant will have vertical asymptotes. And then if you guys are thinking about it, well, wait a minute. If cosecant is 1 over y, did I say it backwards? If cosecant is 1 over y, then secant is 1 over x, the other guy, which means he's going to have his VAs when x equals 0. Wait, tangent had an x in the denominator, so tangent's vertical asymptotes will be the same. Secant has the same vertical asymptotes as tangent because they both have over x. Cosecant has the same vertical asymptotes as cotangent because they're both over 1. But the nice thing is, if we just remember that cosecant and secant bounce off their reciprocal functions, then we could, for cosecant, just look at the sine curve. And for secant, we could just look at the cosine curve. And we could say, you know what, instead of worrying about the x's and the y's, couldn't we just worry about the sines and cosines? And look, whenever sine hits the x-axis, what do you guys see popping up out of that intercept for sine? Whenever sine hits the axis, what's popping up?
A line.
Yeah, and what kind of line?
A straight.
A dotted line.
That was my next.
So the hint is that the intercepts, and I could be careful, it's not the x-intercepts, it's the sinusoidal axis intercepts, the middles. Yeah, you guys are good. It's on the recording, I refused to. The intercepts of sine and cosine. Have fun, guys. The intercepts of sine and cosine will be the vertical asymptotes of cosecant and secant. Always. Always. The intercepts of sine and cosine will always be the vertical asymptotes of cosecant and secant. Nick, help them out, okay? The intercepts with the sinusoidal axis of sine and cosine will always be the vertical asymptotes. So could you memorize? And could you set the argument equal to pi n, the argument equal to pi over 2 plus pi n for these as well? I guess, if you really want to. Or you could just graph the sine or cosine curve that you're going to have to bounce off of anyway. Find the intercepts and just mark the vertical asymptotes and forget the whole solving thing altogether. But you got to graph the sine or cosine first.
What's that little U in the ring?
Oh, it's actually a mathematical symbol that means intersection, like union. No, actually, sorry. The U means union. You probably saw it in geometry when you were doing like if-then statements. If P, then Q, like contrapositives and all that stuff. That's okay. That's okay. The U though stands for union, which just basically is the mathematical symbol for or.
Okay.
Just means or. But technically, if you guys ever put a comma, I'll probably count it right. Or you'd be like, oh, this comma as well as this kind of means the same thing. All right. So if I were you, and if you're a highlighting person, for tangent and for cotangent, we highlighted the vertical asymptotes, and then remember, oh, the poles are halfway in between, and then we either tangent is an optimistic person or cotangent is a pessimistic, unless someone gets flipped, reflected. For cosecants and secants, I would basically highlight two things. Bounce off. And the intercepts of sine cosine are the vertical asymptotes of cosecant and secant. These are true, but you don't have to solve for them the same way as tangent and cotangent if you can get your sine or cosine first. So for cosecant, we're going to look at the sine. For secant, we're going to look at the cosine. And that should follow from the formulas that you guys memorized in chapter 4a, where we said cosecant, the quotient property, no, the reciprocal property, sorry, is 1 over sine, and secant is 1 over cosine. And that's also important to know because like yesterday in your calculator, how could you graph a cosecant curve? You had to do 1 divided by sine. There was no cosecant button. You had to know it's 1 over sine. And same thing with secant. How do you graph them? You have to do 1 over cosine. So I would love to practice this. Do you guys have the idea? Should I dual page it? A few of you are still writing. Because we need to get an example of this. Once again, all of these things are good as far as memorizing, but if you are good at, or if you can get good at, graphing sines and cosines, you actually get to skip a lot of the steps that you would have to solve by hand otherwise. So here's the idea. My little quick way of writing it. Maybe you need to write it, maybe you don't, from what I wrote over there. Long story short is if you ever want to graph a cosecant or secant curve, make it a sine or cosine and graph that first. But when you graph your wave, you have to make your wave dotted because that is not the cosecant secant. We're just going to use the wave in order to bounce off and mark our vertical asymptotes. We're going to use the wave for the cosecant and secant. So as an example of that, I don't know if you guys can see it, it's probably kind of small. Hold on. There we go. For those, it's kind of hard to see. Oh, come on, you do that with your phone sometimes too. We're trying to graph this guy. 2 cosecant of x plus pi over 4. Are we gonna go straight to the cosecant? And the answer is no, not unless you wanna start solving for all sorts of crazy stuff. Instead, let's say, wait a minute, I know cosecant. He's the reciprocal of sine. So I'm gonna say, okay, cool. Sketch first, before I go straight to the cosecant, sketch, what if this was a sine instead? And if it was a sine instead, wouldn't I technically do 0 plus 2? Right? To see my sinusoidal axis, to see my d. So I'm going to go ahead and really quickly say, wait a minute, if I was graphing sine, I would want to know, or want to think about at least, how d is 0. My b is 1, because there's nothing next to that pi. Sorry, nothing next to that x. And now I can see my d, my a, my b, and my c over b. And now I can think of all those things that we did with a sine curve. For instance, I can say, hey, I know my sinusoidal axis is d, which is 0. I know my amplitude is 2, the height of my wave. I know my period, oh stink, we gotta find him. Wait, it's not bad. Does anything change if b is just 1? No. Okay, so 2 pi over b, 2 pi over 1, my period is still just 2 pi. Now where's my initial point? Do you remember this one? It's been a while. 0 would be the y value because sine starts in the middle, which is d. D is the y value. Yeah, it's at y equals d. So I stole the d for the y, but what's the x?
C over B.
C over b. But wait, careful, isn't it minus c over b?
Yes.
So it's not pi over 4, it's negative pi over 4. Is that good? Shift it to the left, right? Plus we shift to the left. Okay. So then I'm going to go ahead and put all this together to get my sine curve.
Okay.
Now, to be honest, as you get better at it, if you're graphing secant and cosecant, the less you write down, the less complicated it's going to look. I'm going to actually do all of my sine work in the red, and I'm going to go over for the cosecant and secant in a different color. Because all of this stuff, the green and the red, it's technically not the actual graph of secant, only the blue up and down is. That's secant. If you guys remember yesterday, all of that was gone. So whether you do it in like a pencil and then show your cosecant with a pen, whether you do dotted everything and then do solid of the graph, somehow distinguish, because secant and cosecant should not have anything inside when we're actually looking at their graphs, but we have to use the inside to help us. So here we go. I'm going to go ahead and show my sinusoidal axis. I'm going to go up 2 and down 2, right? Once again, none of this is the cosecant yet, but we're going to use it. I need negative pi over 4. Ah, stink. What's my quarter cycles? My tick marks? I need to figure out my tick marks. 1/4 of 2 pi. Isn't that pi over 2? Oh, stink. Pi over 4 and pi over 2. Okay, well, that's the same thing as 2 pi over 4. So I can actually kind of go by pi over 4s and just think every key point will be every 2. Josh, are you awake, bud? Okay, go ahead and take off your hood and then make sure you're eating. So negative pi over 4. Hold on. You guys see how I'm starting to get my initial point? I just gotta make a tick mark. Just gotta get a tick mark. Negative pi over 4. I can mark my initial point, right? Okay. Every quarter cycle there's a new key point. Follow the flow. Sine starts in the middle and then goes up. But how many tick marks do I have to go in order to get to that top?
2 pi over 4.
Does that make sense? I have to go pi over 2, so I have to go 2/4 to get there.
Okay, I get it.
2/4, now I'm at the top. I have to go 2 more fourths to get to the middle. 2 more fourths to get down. And 2 more fourths to get back up. Because my quarter cycle, to make it last 2 pi, I can't go every 1/4, I have to go every 1/2, which is, okay, I have to go 2/4 tick marks. 2/4 tick marks, 2/4 tick marks. And in case you're confused why, I had to get a common denominator to be able to compare the two. So then that would be pi over 4, that would be 3 pi over 4, that would be 5 pi over 4, oops, 4, and then 7 pi over 4. Okay, here's my sine curve. Wait, why am I making him dotted again?
Because it's not the actual graph.
It's not the cosecant, right, but I'm going to use it. Get that sine curve. Spend a lot of time on that sine cosine section to help us. Now, look at your clues. 2 things, vertical asymptotes and bouncing, basically. Vertical asymptotes and bouncing. How am I going to get my vertical asymptotes? Because I'm now going to the cosecant part. What do I look at? Here's my sinusoidal, here's my middle. Where's the middle? Right here. Okay, cool. Make that a vertical asymptote. If I needed to write it, cosecant will have a vertical asymptote at x equals negative pi over 4. But are there more vertical asymptotes?
Yes.
Yep. Here's one at 3 pi over 4. There's another one at 7 pi over 4. Another way of writing this, if you had solved it by hand, would probably be negative pi over 4 plus pi over 2 n. Nope. Plus pi n. If you had solved for it, if you had actually done all the hard work, you could have gotten this little formula and you would have started here and then gone pi, which would have been 4/4, pi, 4/4. You could have solved for it, or you could just look at the intercepts and say, hey, there they are. Now, what's the bouncing thing? What's going on with that? In between the vertical asymptotes, what does the cosecant do? Comes down, bounces up. Comes down and hits a max and goes back up, or comes up and hits a min and goes back down. So let's do that. Here's a max. So my cosecant's going to come down. If you want, you can actually mark that point. It's going to bounce. There it is. It's going to hit the min, it's going to come up, and then it's going to bounce. Question, could I get more of these if I wanted to? Yeah. What would I do to my wave? Keep going. And what would I do to my pattern? Keep repeating. But my cosecant, if you were to put it on your calculator, remember when we first graphed a cosecant or secant? I think we graphed a cosecant. Yesterday, remember how it just looked like those little ups and downs?
Yes. Looks like teeth.
That's where it comes from. Oh yeah, kind of.
So, like, the vertical asymptote is basically anything that hits the x-axis, right? Like a point that's on the x-axis?
On this one, it was the x-axis, but in general, it's always the sinusoidal. Because if that shifts, then the vertical asymptote won't be when it hits here. It'll be like if this is all shifted down when it would hit the sinusoidal
So
wherever it
this
is.
one is just easy.
Yeah.
Thank you.
But, remember, if we're graphing the sine and cosine the way we've been doing, don't we always have that middle
Yeah,
line? So it's whenever it hits the middle.
okay.
Whenever it hits the middle.
Yeah, hopefully.
So long story short, for cosecant and secant, what do we have to be really careful and do first?
What?
The sine or cosine?
What was that?
That's them being them.
I
Okay,
don't know what he said.
there's one more thing.
What is that?
One more. Whoa! What's that?
Oh my, it looks like a
Not, it looks like a spider. No, I would not have put the spider. Okay, hold on. I want you guys to grab, you can't see. I know. It's so exciting. Hold on, pause. Let's see if you can get it in your calculator. I'm going to write a function for you. I want you guys to write down graphing. Let's not do it. Calculator's out. You got it. Graph f of x is equal to x sine of x. If you think about it, in real life, waves, mathematically so far, sines and cosines, don't they just keep on going and going and going and going and going?
Mm-hmm.
Is that realistic in real life?
No.
Because if you drop a pebble in a pond, what's eventually going to happen? The ripples are going to stop, they're going to smooth out. So if we're trying to talk about some real life examples where the waves don't stay at the exact same amplitude the whole time, whatever that time is, we have to figure out, okay, how do we change or what do we add? Well, not add, that's translations. What do we include to change the heights of the wave. Well, guys, look at that picture. Aren't the heights of the wave changing?
Yes,
All right, cool. What's new?
there's another.
There's an x multiplied on the outside.
That's there's an E too.
I want you guys to get this one in your calculator. See if you can make it match. Hopefully you're in radian mode. Zoom standard should be fine. And if you get this one to match, why don't you go look at this guy? And I want you to see, can you find a pattern as to what is happening when we take a wave and multiply it, take a wave and multiply it by somebody else? We're trying to ask ourselves the question, what pattern is happening? There is a pattern. You're multiplying by two very different things, so it'll change it differently, and yet something is the same. Don't contrast. They will look a little bit different, but compare. What is similar?
Oh, you said my battery.
You figure out what's going on.
There seems to be something wrong with the graph.
Amen, brother.
We
Ooh, yes, white space.
Did you guys grab the second one too? It's changing too, right? It's not staying the same height. Yeah, that's crazy, right? What's going on?
It's going nuts.
Okay, I don't have a calculator. And to be honest, I haven't graphed this, well, I guess in honors I did it, which would have been like a week or two ago. Anyway, coming back.
They're that far ahead?
Leave it for me.
We can borrow.
Coming back.
Who died?
Here we go.
What?
Ready? Sine starts in the middle, right guys? Sine starts in the middle. Question, for this guy, I know what sine does. He goes up and down and back up again. I know what e to the negative x does. And I'm going to put those two together and say, you know what, I bet for this one, I bet he's going to be doing something like, what do you guys think?
The heartbeat monitor that went flat.
My careful in a pond that is leveling out.
Can you take a walk outside?
Okay, I heard.
Okay.
That was mean. Wait, what?
Okay.
Whoa.
What's going on?
If you guys look at your calculator, it gets really small really fast and really big really fast. Because, ready? I know who e to the negative x is. And e to the negative x is a swoop, ooh, that's been flipped. E to the x is a, sorry, e to the negative x is a swoop that's been reflected.
Okay.
Wait a second. Wait a second.
Yeah.
How did you get that?
I remember it.
Yeah, that's just too cool.
I deserve to get this crazy.
But wait a minute, hold on. Wouldn't it go down forever? There's nothing limiting. Oh. This is y equals e to the negative x. Now I can do y equals negative e to the negative x. Because sine goes back and forth between positive and negative, he'll be flipping that guy's signs too. And then you'll have x.
Oh my god.
Now pause, look at this guy. Look at this guy. The sign is being held back.
He's like a lot.
The sign is being held back by y equals x.
Bible.
And the sign is being held back
Yeah.
by y equals negative x.
Actually happens easy.
This effect that happens by multiplying a wave by another function that will limit it is called damping functions. Like a damper, yeah. Or if you're dampening sound, etc. Like if you put insulation in order, like, I don't know what they're called. When like you have drums like up on the stage, they're trying to like dampen the sound, they have that wall around it. What's that called? You guys know what I'm talking about? Anyway, they're trying to dampen the sound. Oh, it's important.
Yeah, I think I broke the wall.
Yeah.
Where's the water?
Right.
So wait a minute, can you guys think of, hold on, pause, what's another function besides an x, besides an e to the negative x? Why don't you try something new? And why don't you multiply sine by something else? By maybe an ln of x, maybe a log of x, maybe an x squared or an x cubed. You can have it being held back by other guys as well. Now, guys, this page, It's not necessarily, hold on, pause. This page isn't necessarily a huge memorizing page, but it is like oh, hey, there's a lot that we can do with waves. And in nature, if the ripple levels out mathematically, we can do something like that to help it out. Sines and cosines are the waves. We have to include other functions in order to make a formula. All right, okay, with this. Homework postings due tomorrow.
Where's mom though, George?
You guys have 15 seconds. Enjoy them.
So it just makes it bigger.
Bye guys, see you later.
I can't remember it.
Because I had to print out.
And when he does that, that's
GTV merging, right?